Hi, we're going to be talking about section 3.2 from your book, differentiability. We're going to look at when does a derivative not exist, when just some different definitions of differentiability, like meaning it's locally linear, that it means it must be continuous if it's differentiable. We're going to look at how to calculate derivatives on a calculator, and the intermediate value theorem for derivatives. This should be a pretty quick video. Well, you'll have to pause it and do some work, but as far as the video, it should be pretty short. Where does a derivative not exist? So you can read this basically, if a function is not continuous, then it is not differentiable. So you could think of the step function at each of those steps on the step function. It's not continuous at those steps, therefore it's not differentiable at those steps. Even though you think of a step function and derivatives are just slope, and the slope of each step is 0, so you would think it would be okay, but because it's not continuous, there is technically no derivative at each of those steps. The second part and third part are kind of close to the same thing. The derivative does not exist at a point if the derivative from the left is different from the one on the right. In other words, it makes a corner. So the absolute value is function is a good function to think of with that, where you have, let me see if I can draw. Right there we can see the absolute value looks like it has a slope of -1, and then it jumps right at 0 to a slope of 1. So at 0 the derivative does not exist, because the derivative from the left, which is -1, does not equal the derivative from the right, which is 1. A cusp is kind of the same idea, except it's going to be more in the shape like a bird. You know, those little birds you can draw like that. Anyway, where it approaches, the slope from the left approaches -infinity, and from the right approaches +infinity, or yeah, that's right. Then that's a cusp. So same sort of thing. 2 and 3 are the same thing, and below here it says can be summed up graphically as any pointy place. So if there's a pointy place on the graph, their derivative does not exist. Also, a derivative does not exist if the secant lines approach infinity or -infinity from both sides. Another way of saying that is if there is a vertical tangent line at some point on the graph, then there is no derivative at that point. Okay. I want you to try this. Where does the derivative of the absolute value of x plus 3, that quantity is the absolute value, plus 2, where does it not exist? So if you have to, you can graph it, but try not to. Just try to use your brain. Hit pause. Okay, hopefully you know that this function is just the absolute value function, and it's shifted. That makes it left 3 and up 2. So we'd have our function here, left 3, up 2. Absolute value would look like this. So where does it not exist? Oh, I didn't draw a very straight line there. That's all at -3. So f does not, or f prime of -3 does not exist. Okay, so the derivative of f at -3 does not exist. Hopefully you got that. Okay, I want you to hit pause and go through this whole exploration. It's actually really neat. It'll take you through, just follow step by step and write down the information and any notes that you want. Try to really at the end of this, write a little 2-sentence summary of what you learned through this exploration, just to try to organize your thoughts a little bit. So go ahead and hit pause. It's pretty cool. Okay, moving on from there, how do we calculate derivatives with your calculator? There's a function called nderiv, or nderivative. So if you were trying to find the derivative of f at a, you would do the nderivative function, and you'd type in the function f of x, and then you'd do the comma, and then you'd say in terms of x, comma, in terms of whatever a is or whatever the number is. So, for example, to calculate the derivative at 2 of f, when f of x equals x cubed minus 3x, on your TI-84 you'd hit the math button, then scroll down until you hit n derivative. I think it's 6 or 7 on there. Select that one, then type in the function, so you type in x cubed minus 3x, then you do comma, and then x because you're doing it in terms of x, and then comma, you're doing it at 2. The function that the calculator actually runs here is it types in whatever your function is, it puts in 0.00 to the right minus 0.001 to the left, and just averages those points. So you're really just finding the slope using the average, kind of the same way we've done, mostly the same way, except when we've done the limit for h, we usually just go to the right a small distance. So this is going to the right and to the left. That should just give you a better average. So when we do that with this function, I wrote out what the calculator will actually calculate there, and it should give you an answer of about 9. It might have a decimal point or something after it, 0.00 something, but that should be pretty close to what your calculator gives you. So I want you to try, go ahead and hit the pause button, use your nderivative function on your calculator to calculate a f of x at x equals 3, b a different f of x at x equals negative 2, and c a third f of x at x equals 3. After you hit pause, I want you to think about these and see if they make, well, after you calculate them, see if they make sense to you and see if there's any questions that you have. Okay, hit pause. Okay, so hopefully you got, for the first part, let's see, the derivative would be 4 minus 2x, so we plug in 3, we get 4 minus 2 times 3. So you should have gotten, hopefully your calculator did negative 2 for your value of the derivative at x equals 3 for the first one. On the second one, think about this, what the shape of this is. This is a line with a slope of 3. So it doesn't matter where you do it, your calculator should give you the slope to be 3 here. So hopefully your calculator gave you a 3. For the third one, your calculator probably gave you the derivative of f of x as the absolute value of the quantity x minus 3 to be 0. But if you think of what we already defined, absolute value, this function, if you were to graph it, is just over 1, 2, 3, and looks like a pointy place at 3. Therefore, you have to be super careful with your calculator when you're using it, because it will give you the wrong derivative. There is no derivative at this point. Okay, it's a cusp or a pointy place, so it's or a corner, I guess this is called, not a cusp. It's a place where the derivative does not exist. So be really careful. Like I said, your calculator will calculate the average of those two lines right there, and it's true. If you were to do that formula we did before, typing it in here, you'd get, a -1 plus 1, average those two, that averages to a slope of 0. So your calculator did the algorithm right, but we know that the slope does not exist there. So end derivative is powerful, it's wonderful, it's fast. So if you can use your calculator, obviously it's nice, but make sure you're thinking about what the function is, what it looks like. Is there a cusp? Is there a corner? Do the derivatives from both sides equal the same amount? Or is there some sort of vertical tangent line there? Or vertical asymptote. We can't have a vertical asymptote either, so just be careful when you're using it. Like I said, great tool, wonderful most of the time. You can also use end derivative if you want to graph a derivative. Just go to your y equals, do end derivative, type in the function in terms of x, so you just do the function comma x. It should graph the function or the derivative for you, so that's kind of a neat thing. If you want to give that a shot, hit pause and graph one of these on your calculator. The easiest one, if you do part B, you should get that graph of just a horizontal line at 3. Should be pretty easy for you. Okay, finally, differentiability implies continuity. So if we know that the derivative of f at x equals a exists, then f is continuous at x equals a. I think that makes sense. It has to be continuous in order for it to be differentiable. Or if there is a derivative, then it would obviously have to be a continuous function. Does not necessarily mean in the other direction, like absolute value, we know is continuous at 0 here, but that is not differentiable. So it goes one way, this isn't something that goes both. The second theorem here is the intermediate value theorem for derivatives, and it just says that if you have some function f of x that's differentiable from a to b, then if we know f of a, the derivative at a of f and the derivative of f at b, so let's say it was -1a, so basically f had a slope of -1a, and then it has a slope of 5 at b. It hits along that way from a to b, it hits every value between -1 and 5. So it would have to hit a slope along that whole thing. Now it can change a bunch of times. It could go up and down and up and down and up and down, but somewhere between point A and point B, it hits every value there. So like I said, if the slope was -1 and then it was 5, anywhere between there, it's every number between -1 and 5, somewhere along there, at least once. So that's all Theorem 2 talks about. That's really all you need for 3.2, so bring in any questions you have. Thanks.